Ok, escuto pássaros. Só pode ser teu, Henrique, mais ninguém.
Good morning, Professor Lemos. You are listening?
Hello, I'm okay.
We are already streaming on YouTube, and after introducing the session, I will start to play the videos.
Okay, just a minute. I've got to start the session. Who is in the session?
We got a list of attendees for about 12 persons.
All right, do I have 12 people there?
Yeah. Can't you see the list of members?
Let me see. Where's the
on
list?
The left, on the
oh,
left.
Yes, on the left. Okay. All right, good. All right. So I'm not muted now, Enrique. All right. I'm fine. Thank you. All right. Okay. So let me start the session. Welcome everyone for this session. It's part of the main track of LADC. So we've got 4 papers in the session. So how it works is that we're going to play recordings for each of the papers. I think the recordings are ready. And we're going to allocate 5 minutes for questions at the end of each presentation. All right. So, it doesn't quite add up, all right, but we hope that magic will happen. You know, we can fit 4 presentations of and 4 or 5 minutes. It will happen something, all right. So you've got 4 papers today. The first paper is fault injection platform for affordable verification and validation of CubeSats software. The second paper is revocation mechanisms for blockchain application review. You've got the 4th paper, an algorithm-based fault tolerance strategy for the BitTonic sort parallel algorithm. And the last paper is the feature rankers to predict classification performance of unsupervised instruction detectors. All right. Based on this short presentation, and welcome, I request that the first video is started, please.
Good morning. My name is Enrique. I'm professor at the University of Coimbra, Portugal, and I'm presenting the paper Fault Injection Platform for Affordable Verification and Validation of CubeSat software. This work has been done in the context of the ADVANCE project, which is a European project involving several partners, but including University of Coimbra and IMP. IMP is the National Brazilian Institute for Space Research. The outline of my presentation is this one. I start with the problem and presenting our approach. I describe briefly the tool, and at the end I'll show some preliminary results and some conclusions. Well, CubeSats and all sorts of small satellites, as you know, are an important trend today. In CubeSats, more specifically, they have been started as a pedagogical and scientific initiative, but today they are much more than that, and a lot of commercial and very important applications are being developed using CubeSats. CubeSats are very small satellites, 10 by 10 cubes, and you can put several cubes together to build larger satellites. But what is really important for this presentation in CubeSats is that CubeSats are made of commercial off-the-shelf components, normal components. And this is the big advantage of CubeSats, because COTS components are very cheap compared to space-hardened hardware. They have a much better performance. The same for lower consumption, and very important, they are very easy to buy, which is not the case of space-hardened hardware. But all these advantages came with a price. COTS components are designed for Earth conditions, not to the difficult space conditions. So they are quite sensitive to space radiation, and space radiation causes single event effects. Single event effects are a big group of, let's say, bad things that can happen after space radiation or in the consequence of space radiation. But the one that I'm really concerned with is single event upsets. Why? Because this is by far the most frequent consequence of space radiation. So you can think about single event upsets as events that generate hardware transient faults. So hardware transient faults in the boards of a CubeSat, in the computer board, or in the payload, in the satellite control board, or in the payload board. So obviously, we are sending satellites with normal components that are not prepared to cope with space radiation, and we may have a lot of questions. First one is, what is the impact of single event upsets on the software running on the CubeSats? And this question can be detailed in a set of much detailed sub-questions that we can ask. But another big group of questions is about whatever we can do to improve resilience of software in CubeSats. Obviously, because the idea is to keep the big advantage of CubeSats, which is normal hardware, and everything we want to do is at the software level in order to increase resilience. So the proposed approach, we start with a very old thing, which is fault injection. Fault injection is not new. It has been used for decades. And in this new context, we are actually proposing fault injection, but to be used in a new way. Well, the two big parts of the utilization of fault injection are still there. On one hand, we use fault injection to evaluate the impact of single event upsets, concerning failure modes, and the integrity of key elements, for example, the real-time operating systems, or very detailed things such as error propagation. This is typical in fault injection studies, and obviously to evaluate whatever software implemented fault tolerant techniques you could add to the software. But what is new is we are not using fault injection to evaluate the boards of CubeSats or the CubeSat. The target is the software. And the software, and we are proposing a new thing, which is fault injection as part of the software development lifecycle in CubeSats. So as a part of software testing and verification or validation. So actually software testing is to, the idea is to test your software against all sorts of possible inputs. We could take the faults caused by space radiation as a kind of an extra input, and that is the role of fault injection in our approach. So why software is the main target? We know, actually everybody knows that the impact of hardware transient faults is highly dependent on the software. And just to give you an example, and this example is interesting because it is very similar to what we are doing with IMP. This is one of the results of fault injection campaigns we did many years ago, almost 20 years ago, in a project, in a NASA project called Remote Exploration and Experimentation. And in this project, actually, NASA's idea was to send normal computers to space to process, as a payload, obviously, to process data, especially heavy data from sensors like cameras, in order to select the best data to send down on Earth. Because in far regions of the solar system, the speed of the communication with the satellite is really very low. So it is important to select the best data to send down. And that was the idea. And NASA wanted to know if could rely on a normal computer as a payload to process data in this difficult environment like in space. And as you can see in this experiment, we have 3 different applications, and even the operating system crashes are very dependent on the application running on the software. But for example, concerning the failure modes of the application, for example, wrong results, which is a very important failure mode, in the Pi application, more than 50% of the faults cause wrong results. So the application terminated, everything looked okay, but the results were wrong. But for example, in the gravity, only 3.2%. So it is really very important. If you are developing your software for CubeSats, it is important to know if your software is more like gravity, not particularly sensitive to radiation, or is more like pi, very sensitive. So this is why the software is the target. And obviously, if it is very sensitive, it means it is mandatory to do something to improve resilience of the software. So our proposal has two steps. First, we propose to verify the impact during the software development process, just to evaluate if your software is very sensitive or not. And assuming that you need to add software implemented fault-tolerant techniques to your software, the second step is the validation of that of those fault-tolerant techniques in order to be sure that your satellite is resilient enough to fulfill the missions. I'm not going to detail the software implementing fault tolerance techniques, but there are a lot and they are very well known. So the idea is to use them. For example, we can detect errors and then recover using well-known techniques, or we can simply re-execute the software and compare the results of two re-executions to be sure that everything is okay. So we designed a new fault injection tool called CubeSat FI just to make this possible and very practical. These are the goals of the tool. So pretty standard goals: emulate transient hardware faults, compatible with CubeSat boards, all CubeSat boards, provided that the board includes JTAG. This is important because we are using JTAG as an entry point to inject the faults. JTAG is a standard that most of the chips have today. Imagine, for example, the processor chip. So what you can do with JTAG is to stop the processor for a moment, collect the information using the JTAG port, the key information, the content of resistors, and then you can change a bit and put back again and let processor go. So in this way, we insert a fault, an error without, in a very simple way. This is used for debugging, by the way. And the rest of the fault injection goals are similar. Generate campaigns, and inject faults automatically, and get the results to analyze later on. This is the image of our setup. So the injection runs in the host computer, this laptop here, and this is one of the boards, the target boards, EDC. And this is a small board. Remember, it is a CubeSat board. And EDC is environment data collection, is one of the boards developed by INP as part of the Brazilian environment data collection system. And everything is controlled by the host computer. And to show you the profile or the workflow of fault injection, the host computer, in order to inject the fault, resets the target, the board, the CubeSat board, and then wait until the system is running normally, and then you have the injection window. Faults are injected here, normally at random, and then you have the observation window. You wait some time to observe the effects of the fault, and then you store the results and reset the system again to inject the next fault. So this is the aspect of the user interface of the tool in order to define campaigns, configure campaigns, define faults, reset the parameters, and then the tool generate the faults automatically according to the parameters. For the time being, we are injecting faults in the processor register. And this is another screen showing the dashboard to control an experiment. So you can pause, you can abort, and you can see what is going on. So let's see a very brief example. Remember, this is the board, but the real target is not the CubeSat board, it is the software that is running on the board. And this is the key aspects to define a campaign, a workload, that is the software that is being tested, a set of faults, and what we observe. In this case, we are just observing the failure modes, what happened to the software globally. I don't have time to detail this, but basically we inject two sets of faults, and at least the first one, the goal was to reproduce random faults. So any resistor, any bit of the resistor can be affected at any time. Here are an example of the big results. What the software that decodes messages in LADC does when there is a single event accept. Actually, 84% of the time does nothing, so continues normally. This is pretty common, and in the next slide you will understand why. But in the other case, you have other failure modes. For example, wrong results, which is a very difficult to cope with failure mode, was the percentage of this type of failure modes was very low. But remember, other software applications may show a very high percentage. This is a particularly bad failure mode because it is a kind of silent data corruption. Here you can see some detail on what happened when you inject faults in different resistors. The blue bars represent the no effect failure mode. Nothing happened. So as you can see, for most of the processor resistors, when you inject the fault, nothing happened. And the reason is very simple. Is because the software is not using these resistors, or the compiler is not using these resistors in the software. For example, R7 is heavily used, and as you can see, most of the fault produce really bad effects. And obviously, resistors such as the program counter, the stack pointer, or the flex resistor obviously have a huge impact. So this is one of the reasons, maybe is the most important reason why software is so determinant in the effect. If your software is more complex and the compiler needs more resistors, then your window of vulnerability is much wider. So you need to verify the sensitivity of your application before deploying the application to space. These are more results. Lack of time, I'm not going to show, and then jump directly to the conclusions. So CubeSat is a fault injector, not very different from other fault injectors. This is something the CubeSats can be used in any board, but the key idea is not in the fault injector. The key idea is in this approach that proposes fault injection as a key element in the software development pipeline in CubeSats. So in the first instance, when the program you are developing for the CubeSat is ready to test, you need to perform fault injection to evaluate the sensitivity. If the program is quite sensitive to software faults, to faults produced by radiation, you need to enhance the program with software implemented fault tolerant techniques. And then as a second step, validate that the enhancements you did in the software are really solving the problem. And this is, in a nutshell, the key idea. As a future work, or currently, we are developing more fault triggers, more fault types. We are formalizing this approach of embedding fault injection as part of the software development process for CubeSats. And we are planning experiments to demonstrate that it is possible to make CubeSats really resilient to space radiation using software-only fault-tolerant techniques. And that's it. Thank you for your attention. And we are available for questions
at any time. You can send an email to any of us. Thank you.
To any of us. Thank you.
All right. Thank you very much for the lovely recording, Enrique. Are you listening to me, Enrique? Enrique, I'm talking to you. I'm talking to Enrique, but Enrique is not listening. Is anyone listening to me now, or is only me?
I do hear you.
Okay, so is Enrique not listening to me? It appears that you are offline, Enrique. With Regina. Okay, guys, you're losing time here. Brilliant. Okay, can you unmute yourself?
Hello. Can you hear me?
Good. All right.
Can you hear me?
Yes. Thank
Great.
you,
Great.
Enric. Okay, I'm asking the audience. Thank you for the talk. All right, brilliant. So for the recording, any questions? I've got questions always. Any questions? Anyone want to ask questions? I've got a question, Enric. Enric, it's quite interesting your idea of using fault injection at changing, as you say, the pipeline of development process. All right. So, and I've got several questions here, but I'm going straight right to my last question. You have seen test-driven development. All right. So, how you see fault injection driven development?
That's a quite interesting idea. Yes, well, maybe in this context that makes perfectly sense, because in what we know is that single event upsets in space really affect the hardware, but the twist is not looking into the hardware, because we want to use the hardware as is without anything. So the twist is just look at the software, knowing that making the software robust is essential, and fault injection is a kind of a tool to do that, because we can accelerate. So I see perfectly sense in your suggestion. So maybe that could be a good idea for the step we are taking now, which is try to produce a formal approach to how to change the software development process, and exactly in which steps we should introduce the fault injection, and the way fault injection can be used. You are quite right, because actually fault injection, we can see it as a testing tool. Actually, what we are saying is, in addition to the normal inputs that you do in functional testing, we have a pretty common input in space, which is transient faults caused by space radiation. So that is part of the test. Is part of the test, and in order to test that too, the idea is to use fault injection. So if you let's say create the context in that way, fault injection driven testing approach, that makes perfectly sense. Thank you for the idea.
No, I want my royalties on that. So anyway, so yes, because it changes everything, because you have got to your fault model right from the beginning, and instead of having the test right from the beginning, you've got to apply the faults all the time, all right? Until your software passes the injection.
Exactly. So the issue is whether it is possible or not to make the software fully robust or fully resilient to space radiation. And one thing is to work on payload boards like this one. That is, it is not the control board of the satellite, but the other thing is the control board of the satellite, where timing issues could be important to control the satellite attitude or something like that. So things may be a little bit more difficult in that respect. But I think for payloads, this could work, because what we know from the past is that software implemented fault tolerance works very well. Obviously, we know that we are causing more. We need more time to execute, because we have software redundancy. We spend more energy because we are executing, for example, different versions. But in most of the cases, that is not a problem in satellites.
Okay. Fine, Rick. Sorry, it's time to. You're very tight. Okay. You're very tight on the thing. It was a very good presenter, very good recording. All right. I'm sorry for the sounds, but let's move on. All right. Thank you, Rick. All right.
Thank you.
All right. Bye. So there is the second talk is revocation mechanism for blockchain applications, a review, and I request that the tape is the tape, no, that whatever is played there, please.
My name is
My name is
Fernando. I'm
Fernando. I'm
studying at
studying at
University of
University of
Coimbra, and
Coimbra,
I will be
and I will be
presenting the
presenting the
research
research
revocation
revocation
mechanism for
mechanism for
blockchain
blockchain
application
application.
a review. I would like to start bring some reasons that motivate our study. As we know, blockchain is a disruptive technology which has immutability as one of its pillars. However, 3.0 applications often need to deal with corrective operation, and this is a great challenge. How to keep the immutability property and allows application to execute corrective operation. Here are some points to illustrate this difficulty. Bitcoin and Ethereum were designed to reverse a transaction. And the second point, there are a lot of bugs in smart contracts. The third point is the revocation problem is a cross-cutting concern across all generation. That means we have problem in 1.0 application, in 2.0 application, in 3.0 application. That's it's explaining by the last point. The technology offers no standard to perform any kind of reversion transaction. Here some contributions. We characterize each identified mechanism according to features, limitation, and areas of application. And we expect that this analysis can contribute to defining new or even improving the existing mechanisms. The mechanisms were classified into three main groups: modification, isolation, and preventing. Modification because they modify or change transactions, modify blocks or change transactions. Isolation because they create a division, keeping the undesirable data outside of the current application context. And preventing because they implement filters that avoid the data be record. Let's start with modification mechanisms. This is the redacting mechanism. Basically, the idea is allowing to change the content of a confirmed block. I prepare here this illustration showing redacting and verifying in two actions. Let's see redacting first. Firstly, here a block N, it has a hash, but when it changed any information, the hash now is different, and the redacting store a new attribute in the block. Some author calls it's a scar, and this is computed using a trapdoor. So combining the trapdoor with the new hash, we have this scar. And the verification process, of course, if we try to perform the current verification process, it will fail because the hash is different now. But the redacting use a different verification process. He computes the block hash, combining with the trapdoor, and check if the seal, the scar, is equal with this calculation. So this is the scar, the seal of the block, and computing the trapdoor with the hash of the block, it's equal, so the block is valid. Here's some characteristics. It is not compatible with the current blockchain architecture. and the private key holder can change any block, even old blocks, and it demands to modify the consensus mechanisms. Here, the pruning mechanism. Basically, the idea is cutting a set of blocks between a path, reducing the size of the network. As you can see, the remaining blocks are connected by a stage area. That means when a verifier checks the validity of the block in the ledger, it must read this stage area. This is an extra step, right? And here some characteristics. Reduce the network size. Removal occurs only on local copies. And it demands to modify the consensus mechanism. This is the erasing mechanism. This method is a kind different because the block must be prepared as a matrix like this. It's a new blockchain design in which the blocks must be prepared to be a matrix, like a matrix, store as a matrix. And there are some indicators for each line and each column that allows to verify each block in the matrix, and if this field validate the block, it's valid. In this case, even removing this block, we can keep validating the remaining blocks because there are a lot of combination here. So this is the way. Some characteristics: no scalable, mainly for public networks. It is compatible with GDPR. And of course, this is not compatible with the current blockchain architecture. Well, let's see the first isolation mechanism. It's accumulator. This is the accumulator. It's a mathematics approach that allows storing multiple information in a fixed size item. Basically, the idea is computing a factor with witness. The factor is the assets, and the witness usually are order data, usually public order data. And in this case, for example, computing this with this witness, it's equal with the previous value stored in the blockchain, so this asset is valid. In this case, we are comparing this set, but the computation results in a different value stored in the blockchain, so this set is invalid. Well, some characteristics: limit storage of information, because there are a limit to be respected. We can't store large data in blockchain. For this reason, costs are unpredictable, but it's a backward compatibility with PKI system. Well, this is a type of mechanism, a public list, in which the application publishes a list with the revocate assets. The lists can follow a scheme, for example, open badge, verifiable credential, and the type of the list, or how the line is represented, can be using a signature, can be a accumulator. The list can be published using a IPFS, for example, and this is a third-party software that can be used to distribute it. And here are some characteristics. Well, it's compromised self-sovereign because to distribute, it's necessary to use a third-party software. And in some cases, the costs are impracticable. In some cases, allow revoking multiple records with low costs. This mechanism divides the blockchain, separating the undesirable data, forking. This technique preserves the integrity of the old records, diverting a set of blocks from the original network, creating a new network. And we can see two examples in Bitcoin when the Bitcoin Cash and Bitcoin Golden was created, and in Ethereum when Ethereum Classic was divided to Ethereum. Some characteristics: creates a new network isolating the revoked records, demands off-chain consensus. For example, in this case was a programmer decision and not a user decision, and keeps the old data. Smart contracts. Smart contracts revoke changing the state of the asset, so this asset can be valid or revoked. The contract just change the state, and the verifying process check the last state if the state is valid or revoked. Some characteristics: it's a no agnostic blockchain because, for example, Bitcoin doesn't implement smart contracts, and of course the trust of revocation status rely on a software such as a smart contract. Filtering. This is the last mechanism. Basically, the preventing consisting in algorithms to prevent storing unwanted data. It's a filtering. It's compatible with any blockchain. Any blockchain can implement it. Has a limited scope action because it's impossible to avoid any data. Well, let's see some summary of the specifications. Here we organize the reactive techniques, and we put here some blockchain compatibilities, the target network, if public or private, if they are compatible with consensus mechanisms, and some reporting validation. And here we created this table to organize features and limitations for each mechanisms: redacting, pruning, erasing, modification. We group here accumulators, list, forking, isolation. We create this, and here features and some applications. And finally, some findings. Well, revocation is an issue that is still open. It's an open field to research. And creating a mechanism that allows to revoke and at some time does not affect the immutability of blockchain, it's a challenge. Regarding a modification mechanism, no work has managed to implement them in a way that is compatible with current networks. The critical issue of this approach is concerned on the modification of the existing consensus mechanisms. And regarding isolation mechanisms, there is always a dependency on another technology. And finally, we see opportunities to combine mechanisms. For example, one can apply preventing with learn machine and publishing a result in a list and record inside the list uh, using an accumulator, and even techniques that demand new designs can be used off-chain, revoking of their environment and referencing the original records to current blockchains using smart contracts to making that connections. And this is the presentation. Thank you.
Okay, good, excellent. Thank you, Fernando, for the talk. And I'm open for questions. Any questions from the audience, which is very passive until now? This is an audience that does not ask questions. Oh, that's good. All right. So, Fernando, I'm going to be straight on this. All right. Why do you want to revoke a block in the blockchain? All right. So, why you would like to undermine one of the basic principles of blockchain? Although in the same, you presented all the challenges there, all right? But nevertheless, you want to undermine something. It's like to build a building without foundations. Let's do the thing without foundations, all right? Always the building will collapse. Right? So what's the motivation of this?
Well, we are motivated because 3.0 application. Of course, we are thinking about cryptocurrency. It not make sense to reverse accredited, but in 3.0 application, we are transferring assets. We are creating registers, and these registers can be wrong, or they need to be revoked. For example, if you created the academic certificate and this is wrong for something, issue process missing, or there are bugs in the software, we need to revoke this asset. So application 3.0 application has this need. So we are looking to this context and try to understand how to create this without damage the immutability.
Okay, so since I think this was fashionable, there's no question still, isn't it? Anyone, any questions? I can carry on the rest of the afternoon here. No questions, no. So I carry on here. Sorry, Fernando. But so why don't you, instead of looking what exists, all right, why don't you propose a new type of blockchain that you allow to do this? All right, because instead of going against the principles of blockchain, since it's fashionable, all right, since anyone can create a blockchain, why don't you create a blockchain which actually is able to do this kind of revoking that you're trying to do?
Well, if I understand, you are asking why not create a new blockchain specifically to revoke, is it?
Yes.
Yeah, it's a good idea. We are thinking about, but we need care about centralization. This blockchain must be public key, and it must refer the original blockchain, and there are some questions, some issues that need to be addressed about this. This is a one good way to think.
Yeah, I think yeah, it might be the case. All right, it might be the case because you've got the freedom to do whatever you want, essentially. All right.
Yeah.
Instead of going against the against the flow, which a lot of people might not understand why it's pursuing something which perhaps for them doesn't make any sense. Your proposal essentially is for revoking, all right? You put the context in which can be applied, all right, and you make a good case for support, and this is it, all right? So that it's your blockchain, all right? You're the owner of a blockchain, all right? There is no questions. There is nothing. There is, oh yes. So there is a question by Luis Antonio Henrique. Very great. All right, I've got a question here. It's unbelievable. I've got a question. So the question asks, does the revocation process need to go through the same validations as the registration process? You understand the question?
The verification process, the same validations. I don't know. I think it's different. I think it's different. For example, in blockchain, there are ways to register harmful data, for example, and this can be a problem. And in this way, this is a different approach to revoke and register harmful data. Is complicated. So in this way, for example, is a kind of different. I think it is not the same process because the revocation can be a more widening. I think it's a process, a more complex process.
Okay. All right, Fernand, thank you very much. Thank you, Luis, for the question. Thank you, Fernand, for the answer. So I think it's time to move on. All right. So this is our third paper of the session. All right. And there is an algorithm-based fault-tolerant strategy for Bitonic sort parallel algorithm. So I'll request that the recording be played.
Hello everyone. My name is Edson. I'm a professor from Federal Technology University of Paraná in Brazil. This work was developed with Professor Elias Duarte from Federal University of Paraná, also in Brazil. And I'm going to talk now about our work entitled An Algorithm-Based Fault Tolerance, a Strategy for the Bitonic Sort Parallel Algorithm. My presentation is divided into 5 main sections. I will start with a brief introduction to high-performance computing and fault tolerance. Then we will talk about the proposed ABFT strategy. After that, I am going to present how the proposed strategy can be applied to make a parallel sorting algorithm fault tolerant. In the sequence, I will talk about evaluation, and finally, I will present our conclusion and future directions. HPC systems are used to execute scientific applications, computer simulations, as well as very large-scale problems. Example, simulations for discover new drugs. HPC applications run on hundreds or thousands of processors, and they are normally compute intensive. These applications can take hours, days, or even weeks to complete its execution. HPC system can be based on massive parallel processing and cluster and grids of network processors. Well, in terms of dependability, reliability is a major issue in HPC. As we know, the mean time between failures decrease as the size of the system increases. For example, Blue Waters, the petascale system of the University of Illinois, has an MTBF of 4.2 hours. There are numerous techniques to make an HPC system fault tolerant. We can see it rollback recover, replication, computer migration, and algorithm-based fault tolerance. Algorithm-based fault tolerance, or ABFT, makes use of properties of the parallel algorithm itself to survive faults during its execution. The algorithm is designed to be resilient. The application must be able to detect or receive fault notifications and adapt itself after fault occurs. So, in this work, we propose a general ABFT technique to make any parallel algorithm designed for hypercubes fault tolerant. With our strategy, developers can employ the proposed technique to leverage any parallel hypercube-based algorithms to survive faults efficiently. The algorithm is able to reconfigure itself autonomously in runtime. Fault-free nodes continue its execution and no work is lost. And the fault tolerance technique relies on the virtual type topology known as the VCube. We describe parallel sorting as a case study. A fault-tolerant version of the bitonic sort parallel algorithm is specified, and its correctness and performance are also presented. The algorithm was implemented in MPI and ULFM. ULFM is employed to handle faults. ULFM is a proposal from MPI forum to handle faults in MPI. Well, let's talk briefly about hypercubes. Hypercubes are intrinsically scalable topologies. They have been extensively used in parallel computing. They organize the communication and execution of parallel and distributed algorithms, and our strategy assumes a logical hypercube. An hypercube can be represented as a graph G. Each node has identifier of length d bits, where d is the number of the dimension of the hypercube. Nodes have unique identifiers, that is an edge between two nodes I and j if and only if the identifiers of I and j differ in a single bit. And a d-dimensional hypercube consists of 2d minus 1 dimensional hypercube. This figure, we see the construction of d-dimensional hypercubes from 2d minus 1 dimensional hypercubes. So here we see 1, 2, 3, and 4 dimensional hypercubes. 4-dimensional hypercubes are constructed with 2 3-dimensional hypercubes. Well, VCube. What is VCube? A VCube is an hypercube when all nodes are fault-free. It is capable of reconfiguring itself as node fail, keeping several logarithmic properties. Our strategy proposed for hypercube-based parallel algorithm involves the VCube in two main ways. Well, the first way, after a node crash, another fault-free node will cover the fault node and execute the task. Nodes communicate among themselves according to the VCube topology in the second way. Well, the topology is able to autonomously reconfigure itself upon node failure. In a VCube, nodes are organized in clusters, which are defined per node. The system is assumed to be fully connected. The communication between two nodes is assumed to be reliable. The fail-stop model is assumed. VCube nodes communicate with a cluster of nodes, usually the first fault-free node of each cluster. And VCube has a function called CIS. CIS is used to determine the nodes with which node I communicates with a cluster S. Here CIS is defined. Here we have CIS for a system with 8 processes. And an example, let's take node 0. And let's take S varies from 1 to 3. C0, 1 returns 1, C0, 2 returns 2 and 3, and C nodes 3 returns 4, 5, 6, and 7. Let's talk a little bit more about our strategy. In our strategy, if node I is fault, then another fault-free node will be its cover node and execute the tasks. we define a function called cover. Function cover returns I covers. Node i's cover is the first fault-free node in CI1. If the CI1 node is fault, then the first fault-free node in cluster CI2 is selected. But if that node is fault, but the second node of that cluster is fault-free, then it is covered. If in that cluster there is no fault-free node, the cluster size is incremented again until cluster CID is considered. A cover node executes the fault-tolerant algorithm as itself and also assumes the identifiers of the node it is covered. For example, if node 0 is fault, then its cover is node 1, which executes node 0's task. However, if node 1 is also fault, then 0 is covered by node 2 because node 2 is the first fault-free node in C02. If node 2 is also fault, the next to consider is node 3, and so on. In this way, a node I can execute the task of up to any -1 fault nodes. If any -1 nodes are fault, the single fault-free node in the system executes all tasks of the nodes. Our proposed ABFT strategy assumes that a cover nodes have access to the data that would be used by the fault nodes. As I said before, we apply our technique to make a parallel sorting algorithm fault tolerant. Sorting is one of the most fundamental and well-studied computing problems, and parallel sorting algorithms have been designed to take advantage of multiple processors to speed up sorting. Next, we show how to make bitonic sort fault tolerant with the proposed ABFT strategy. Bitonic sort is based on the comparison of elements of predefined sequence, which are called bitonic sequence. Comparisons are independent of the input data. A bitonic sequence is a sequence of elements with following properties. There is an index I such that in the sequence is monotonically increasing, and there is another sequence that is monotonically decreasing, or there is a cyclic rotation that satisfies I. For example, this sequence is a bitonic because for I equal 3, here I equals 0, equal 1, equal 2, and equal 3. So this sequence always increase, and that another sequence always decrease. A bitonic sequence is ordered as follows. Initially, the sequence is divided in half, generating two sequences. So the first element of the first sequence is compared with the first element of the second sequence. The smallest element is assigned to the first sequence and the largest element to the second sequence. This method is applied recursively until there are only two elements in each sequence. For example, here we have a bitonic sequence. The bitonic sequence is divided in half. Comparison exchanges are realized. So at the end we have an ordered sequence. The procedure of dividing a sequence of size m into two bitonic sequences is called a bitonic split. The generation of an ordered sequence for a bitonic sequence is called a bitonic merge. Well, bitonic sort can be adapted to different parallel topologies, including the hypercube I described next. The nodes that run the algorithm are organized as a d-dimensional v-cube, where d equal log n. Each node has identifier I. Sort is performed in S rounds. In each round, node I forms a pair with the first fault-free node of cluster CIS. Nodes I and J exchange elements with each other and make comparison based on the elements exchanged in a given round. If I is less than J, Node I caps the smallest elements, and node J caps the largest elements. And at the end of the round, the largest element of node I is less than or equal to the smallest element of node J. So here we can see algorithm 1. This algorithm is the fault-tolerant Bytonic sort with m equal n. So here we have the sequence with same size of the nodes. Here we can see the dimension of the hypercube. So we have the rounds. In the beginning of the round, we have the set of default nodes, and the cover node and the cover function will discover which node will take the responsibility of the default node. The algorithm can be found in detail in the paper. So here we see an example for a sequence with 8 elements. We have 8 processes organized in a hypercube topology. First, second, and third sorting rounds, and at the end of the third round, the sequence is ordered. Well, but also it's possible to order any sequence using this algorithm. So we will see now. Algorithm 2 show the fault-tolerant Bytonic sort for any sequence. So here we have the V-cube dimension, but this algorithm has a new loop. So this loop, but the algorithm also uses the set of fault nodes in the beginning of this round. So a round is started here, and also we have the cover function. So this algorithm is also found in the text. This example shows a sequence. This sequence is not Bytonic. These two symbols represent the comparison between the elements of the sequence. This symbol with a plus inside defines that the comparison should generate an increased sequence, and this another symbol defines that the comparison should generate a decreased sequence. So here we can see an example of execution of Bytonic sort from an input sequence that is not Bytonic on a three-dimensional hypercube. So we hear the symbol. So this symbol means that the sequence should be increasing. It is another symbol that sequence should generate a sequence decrease. We also prove the correctness of our proposal. The fault-tolerant Bytonic sort algorithm completes sorting in log n rounds, even if n-1 nodes become full to run those rounds. The proof is done by induction on the V-cube dimension, and the proof is detailed in the paper. Well, the evaluation. Fault-tolerant Bytonic sort algorithm was implemented in C language, and we use ULFM constructors to handle faults. The code is available online. The experiments were executed on a machine with 32 processors running the Linux operating system. Each experiment consists of sorted 1 billion of randomly generated integers. The total number of nodes n varied from 4, 8, 16, and 32 nodes. Each experiment was repeated 10 times. Results presented are average. A node is caused to crash randomly at any round through the execution of the SIG-kill signal. Well, here we can see the Bytonic sort. Here we have the labels 4 nodes, 8 nodes, 32 nodes, 16 nodes, and 32 nodes. The x-axis shows the fault nodes. Here we have 0 fault nodes, so here the execution of the algorithm with no faults. Here execution of the algorithm with 1 faults for 4, 8, 16, and 32 nodes. Half of nodes are fault here, and any -1 nodes are fault here. The y-axis shows the duration in seconds of the algorithm. So we can see as the system increases faults, also increases the duration of the execution. Conclusion: we introduced a novel algorithm-based fault tolerance technique applied to the bitonic sort hypercube-based parallel algorithm. The technique relies on features of the underlying topology, which is assumed to be a V-cube. In V-cube, if all nodes are fault-free, they communicate according to a logical hypercube. If there are faults, the topology reconfigures automatically at runtime. The technique is based on defined cover, which are nodes that execute the task of those that are fault. The fault-tolerant version was specified and implemented in MPI or FM and executed on 4, 8, 16, and 32 nodes. The algorithm was able to detect and survive faults, not losing any of the work that was done before those faults occur. And as future work, application of the proposed ABFT strategy to other parallel hypercube-based algorithms, to explore other type of algorithms besides parallel sorting, and the development of similar techniques for the shared memory paradigm. So thank you very much for your attention.
I'm mute. Okay, thank you very much for the talk. And yes, you're on time. So with Edson. So yes, you ready for questions? All right. Any questions from this lovely audience that so far has been very passive, except for Luis Antonio Rodrigues? No questions, so I'm going to do my role of session chair. One issue I was looking the paper, I read the paper, part of the paper, and I looked at presentation. But what kind of failures, node failures, do you expect when you execute this sort of algorithm, for example? Right. So what was right? You build your you've got hypercube, you deploy your algorithm there, right? But what kind of faults do you expect to happen in order to require, let's say, a reconfiguration of the structure?
Hello, everyone. Well, in our work, we are dealing with stop failure faults, crash, basically crash faults. So if the process crash, so we apply a reconfiguration according to this strategy.
Okay, so isn't your processes running on the virtual machines or something like that, or you assume it's physical machines?
No, it's a physical machines.
Physical machines. Yes. And all right. So, and you're assuming that there is no communication faults, only in terms of the processes. All right. Okay. All right. Okay, fine. All right, I understand that. All right. So it wasn't because and what we have done essentially is also, to increase the number of faults. All right, and you notice there was some linear. All right, it was kind of linear. All right, the time it takes to execute. Why did you get that? Why didn't you get a more exponential? Or because now you've got n-1 faults, right? You wouldn't expect that the finally, time will be much higher if you got just one node running.
Yeah, that's the algorithmic characteristic. So this algorithm in particular, when you increase the size of the nodes, the hypercube becomes larger, and there are much more exchange between the nodes. So that impacts in the time of the execution.
Yeah, but the case of n-1 in your last diagram, all right, n-1 faults,
Okay.
all right,
Okay.
correct?
Mhm.
All right. So essentially, you've got just one node working there, correct?
Yes, but depends because we inject randomically faults randomically when the algorithm was executing. So the fault could be happen at the beginning or at the middle or at the end. So it's dependent. But you are right. There was only one node executing in some moment.
Okay, but you understand that because it's one node executed in a moment, extent of 32 nodes, for example, all right? The curve is supposed to be something different and not linear. It's basically linear there.
Yeah, we did an average of the
Okay.
time of execution of the main execution. So it happens that a node failed at the beginning or at the end. So we did an average.
Okay, brilliant. So, thank you, Edson. Any other questions? What kind of audiences does ask questions? Edson, I think you've got to have a word with the audience here because audience is not very helpful. All right. Anyway, Edson, thank you very much for your time. Thank you for your talk. All right. And yes, you've got to move forward to the third talk. All right. Let me find myself in my computer. I got lost here. The third talk is okay. Thank you. All right. The fourth talk. Sorry, the fourth talk is feature rankers to predict classification performance of unsupervised intrusion detectors. And yes, so it's yes. So I request, if possible, to play the recording, please. Thank you.
Good morning, everybody, and thanks for attending the session.
Good morning, everybody, and thanks for attending the session.
And
I am Tommaso Zoppi from University of Florence, and I am presenting
mine, Andrea Ceccaretti and Andrea Pontavalli, and the work is about feature rankers to predict classification performance of unsupervised intrusion detectors. Let's get into the topic of intrusion detection. Typically, intrusion detectors revolve around two different approaches. First one being rule or signature based. This approach to detect intrusions essentially rely on the characterization of known attacks for which we derive signatures, and then we compare the current behavior of the system with these signatures of threats, and this allows us to understand if one or more of these known threats are acting in our system, and this way it's possible to detect them. However, this approach is known to be weak against zero-day attacks, because those attacks are novel attacks, and there is no signature which is available for those attacks. That is why, in the last decade, we saw a huge increase, a huge spike in the adoption of anomaly-based intrusion detectors. Those anomaly-based intrusion detectors do not rely on signatures of known attack, so they do not have the concept, they are not tied with the concept of knowing all the bad guys, but they work because they characterize what is normal for a system, and then everything that differs from this normal behavior is considered as an anomaly. The implementation of those anomaly-based intrusion detectors is mainly due to unsupervised machine learning algorithms. Those algorithms are not working as a kind of magic, but they essentially need a precise characterization of the normal behavior of the system to clearly understand where anomalies are. So if during training those machine learning algorithms are not really able to understand what do we mean by normal behavior of the system, it's very likely that we will have a lot of false alarm, a lot of false negatives, meaning missed attack detections, because the model that we learn during training is not robust enough, is not shaped exactly around this system behavior, and therefore it's not possible to efficiently identify anomalies. This is usually due to two main reasons. First one is the attack is crafted very well, so the hacker devises an attack which hides into the normal behavior of the system, and the effects of this attack are not easy to observe. and this is something we cannot really control. The other thing is, when we are trying to build an infrastructure to monitor a system, to understand and to essentially trace the behavior of the system, we are deriving features which are not so informative. Let's have an example. Suppose that we want to set up an intrusion detection system to spot thieves that may want to get into a museum. So here we have the museum. We are buying some monitoring infrastructure, which is through webcams, which we put at the entrance of the museum to see if in the garden around the museum there are some suspicious activities. Now, this data is sent directly to a control room in which there are human operators that are tasked to identify anomalies. So they look at the images of those webcams, which are the features, which provide the features of this intrusion detection system, and then there is the analyzer, the human operator, which is the anomaly detector, which looks at these images provided by the webcams and understands if there are suspicious activities, anomalous activities or not. Now, suppose that there is a thief which gets into the museum from the backyard. Now, webcams are only looking at the entrance of the museum. So this thief is going into completely undetected, and therefore the human operator has no way to detect, to understand that there is a security breach, if we want. So first we have economic damage for the museum, and second, we may have the security head which is firing the human operator, the anomaly detector, because it was not able to detect the thief. But even if we are choosing another anomaly detector, another human operator, they do not have any way to detect this problem because essentially the features of the problem are not informative enough. The webcams are only looking at the entrance. So instead of trying to solve the problem by changing the anomaly detector, I have to focus on how am I going to monitor the system? Because this monitoring system, the features that I'm getting for my problems are weak, and they do not allow to identify the normal behavior, so the normal activity around the museum, and also to spot anomalies. They are just looking at the specific part of the system, which is usually not desirable. Now, we started from this high-level example, but this is exactly what happens when we are devising intrusion detectors for computer-based systems. Usually, we have some data baseline that we can use to try and to train different algorithms. So we spend a lot of time in selecting algorithms, finding implementations, trying algorithms, benchmarking, conducting sensitivity analysis, finding the optimal value for parameters, and then at the end, we end up selecting the best algorithm out of the ones that we tried, but even the best algorithm is not really able to detect intrusions efficiently. And why? This is not because our selection of the algorithm is lacking something, but it's because the data baseline is not informative enough. Therefore, we can say, and we can conclude this example saying that if we don't have informative features, we will always end up in having poor detection performance. Now, this concept can be extended by implementing a function which, as input, it has the quantity of information carried by the feature and outputs a quantitative estimation of the detection performance. Now, supposing that we have this function, it's clear that we can apply this function before selecting algorithms, before losing a lot of time in sensitivity analysis, benchmarking, and this allows to understand if our data baseline and therefore the monitoring strategy for our system and the features we extract from the system are good enough to have satisfying intrusion detection scores. Here you find our approach to implement this prediction function. We start from a dataset, because obviously everything we devise when we want to predict something has to start from some existing data baseline. So each dataset has a given amount of features and a label. So we extract the features from the dataset, then we take and implement some feature ranking or selection strategies that are available at the state of the art and that are usually employed in any data analysis process. So when we have a data set, usually we have a feature selection process which allows us to select the most relevant features that are then provided to machine learning algorithms. In this case, we do not aim at selecting, but we aim at deriving the rank for each feature. So how much each feature is relevant for a given problem. All these ranks are essentially quantities, numbers, that we take together and we normalize in a way that we build an array, a set, a tuple of items that describe the relevance of features for a given problem according to different feature rankers. Now, those are different viewpoints on the same aspect, because all those feature rankers are deriving and measuring how each feature is tied with the label, and so normalizing all these scores and putting them in a more standardized way provides us what we call feature data. Now, this feature data can be used as input to machinery which is essentially effectively predicting the detection performance of a generic unsupervised machine learning algorithm which plays the role of the anomaly-based intrusion detector. Now, it's predicting detection performance by predicting essentially the value of common metrics such as accuracy, precision, recall, Matthews coefficient, area under ROC curve, and so on and so forth. And those machinery are essentially other machine learning algorithms which are not doing intrusion detectors. Those are completely different algorithms which are there as regressors to predict the value of a given metric, taking as input what we call the feature data, or rather the scores that feature rankers assign to each feature in the dataset. Now let's see together an instantiation of this approach. We are taking a dataset, here you find AlphaNet, and this dataset has three features: packets, bytes, and duration. Those features are analyzed in parallel by two different feature rankers, one based on the information gain calculation and the other one based on the statistical chi-square test. Each of those two feature rankers provide a quantity, a number, for each of the three features. So you see that we have two different arrays of three items. Now, each array is standardized, meaning that we calculate aggregate quantities, the best value, the maximum value, and the average of all the three values, here in the example. This brings two results, two quantities for each of the feature rankers, so two results for each of the two, into an array of 4 items that here represents feature data. Now, this array of 4 items is the input to the regressor, which only looking at those 4 numbers, it's predicting the value of a given metric. Here you find examples: FQ score, accuracy, Matthews coefficient. Now, we are almost all set to implement this pipeline of items, because feature rankers is something that you can take from the state of the art. Dataset is something which is either provided by the company or found as public dataset. Normalization step is something that we can implement depending on the specific problem, but we have to devise a way to understand how we can implement the regressor, or how can we use feature data to effectively practically predict the detection performance, so predicting the metric scores. In the paper we commented and elaborated on how to implement those regressors in an efficient way and in an effective way through an experimental process, which is too long to be explained here in detail, but I will try to give you the main ideas. We used 12 public attack datasets 7 different unsupervised anomaly detection algorithms. We calculated different scoring metrics: false positive rate, precision recall, F1, F2, accuracy, matrix coefficient, area under curve for each algorithm on each dataset. And then we had the problem, because for each dataset we are getting just a single data point of feature data. Because each dataset, we extract the features, we calculate the feature ranks, we normalize, and then we obtain a single array of feature data. Now, since we want our regressors to be machine learning algorithms, we know that if we want to train a machine learning algorithm, we want as much data as possible. And in this case, we only have 12 data points, which is clearly not enough. So we created variants of those datasets by slightly changing some attributes of those datasets, and we reached an amount of data points which is more than 100, which is still just a few items, but it starts building a data baseline which is big enough to provide some, at least, initial results. Then we tried different regressors, so different machine learning algorithms, which instead of outputting a class, output a number, and we selected the best regressor out of all the 6 that we tried. We end up building, training, and obtaining a model for regressors for each of the metrics that we find in this slide. This is an example of the data baseline that we use to train our regressors. What we have is a line for each dataset and also variants, which are not reported here for brevity. Okay, so this is the 12 datasets. You find the name. Then we have scores for each of the feature rankers that we use in the study, which are 8 different feature rankers. Some of them are based on wrappers, so they are wrapping other algorithms which provide a ranking of the feature, and this is the case for 1R, random forests, and J48, while the others are filter-based feature rankers which implement some statistical test to devise a quantity which represents how relevant a given feature it is for a given problem, for a given label. Now, those scores that you find here are the scores of the most relevant feature according to each strategy in each dataset. And those are the green ones in the picture. On the right, you find what is called here labels, and those are the values of the metric scores achieved by the best unsupervised algorithm on each dataset. So we have 7 different algorithms. We run all of them on each dataset, and we select the one which is performing better on each dataset. And those are the metric scores. Now, should we aim to devise a regressor for the F1 metric, what we are doing here is we are dropping all the labels which are not F1, and we are providing these as training set to the regressor, and this way the regressor is learning a model which ties the feature data with the label, which in our case is the F1 score. Let's see some results of our experimental analysis. On the x-axis, here we find the F1 value, which was achieved by the best unsupervised anomaly detection algorithm on each dataset or variant. On the y-axis, we find the F1 value, which was predicted by using our strategy. Now, here in this picture, what we have is around 40 data points, because when training our regressors, we went to a 66-33% train test split. So 66% of the whole training data with datasets and the variants, which helped us in performing data augmentation, are used for training, the others for testing. So all the crosses that you find here is something that was unknown at training time and is provided as test set. You see that most of the data points are around the black solid line. This means what? This means that essentially the prediction of the F1 was quite close to the F1 that was really obtained by effectively running unsupervised anomaly detectors. But again, I am recalling you here that this prediction does not require at all to select unsupervised anomaly detection algorithm, training, trying, benchmarking, and so on and so forth. So this prediction is clearly a lot and way more faster than computing effectively the F1 score. We are skipping all the part in selecting, implementing, exercising algorithms. Here you find the result of a different metric, which is the Matthews coefficient, which is desirable to use when we have unbalanced datasets. Because there are metrics such as precision, recall, F1, which are heavily weighted on true positives. So when we have dataset in which we have either a lot of positives or a lot of negatives, those metrics may not be so informative. So in some cases, it's better to use Matthews coefficient. And we see that also for Matthews coefficient, the trend that we are getting is similar to F1. Most of the data points are around the line, which is the diagonal, and since they are quite close to this diagonal, this means that the prediction is quite close to what unsupervised anomaly detection algorithms will achieve after trying, implementing, selecting, benchmarking, and so on and so forth. Okay, so those two slides essentially show that for two different metrics, our prediction strategy was able to predict the metric value with just a small absolute value. Wrapping up this analysis, first, before building the intrusion detector, we have to be sure that we have data baseline with enough quality and enough variety of features which allows us to implement an efficient anomaly detector. So an anomaly detector which is not having a lot of misclassifications. Otherwise, we are just wasting time. We may need to set up, to implement, to benchmark, and to analyze the results of different anomaly detection algorithms, but all of them may be very poor, and this is not due to the algorithm or to the analyst, but it's due to the poor data baseline we have. In such a context, we propose a strategy to predict misclassifications of unsupervised intrusion detectors only using data of feature rankers, which essentially is data which is already available because feature ranking and selection processes usually take part to a generic data analysis process, and this provides, in a very short time, a quantitative measure, an estimation on metric scores that could be reached by a generic unsupervised intrusion detector on a given system. This is critical because it provides a very fast feedback on the quality of data, and it may potentially save a lot of time to the system engineer or system architect. Now, to complete and to extend this work, we are currently working on trying to go beyond intrusion detection. Because all the things we saw in this presentation are tied with intrusion detector because it's our domain in which we performed our experimental evaluation, but everything holds even if we slightly change domain. Any domain in which we are monitoring a system getting tabular data, hardware failures, Internet of Things systems, biometric authentication systems, and so on and so forth, may be suitable for this strategy. And according to our preliminary results also on different domains, we find that this conjecture still holds, meaning that we can predict these metrics values with just a slight absolute error, which is overall desirable. Thanks a lot for listening. I will be happy to take questions. Here you find some works of our research group, and here you find references for different datasets used in this study.
All right. Okay. Thank you, Tommaso, for the recording. You're running quite late on this, and I ask whether there is any questions from the audience, please. If there is no one rising, Tommaso, I was very surprised with your last slide. All right. So you're saying that you're applying the same technique to different applications, different data sets. right? And I wonder, what would you expect your technique to perform in different data sets?
Okay, so first of all, thanks for the question. Now, expectation is that we are getting figures close to the ones that we saw in the slides, meaning that overall we were around an absolute error, which was around 0.1, 0.15 on average for the metric scores, meaning that if really a data set was processed by anomaly detectors and anomaly detectors were getting 90% of accuracy, our prediction technique was saying something between 0.8 and 1. So it
Okay,
was
but
not...
my question, Tomas, is a different question. This is nothing to do with the application area.
Yes.
No, nothing to do with the application area. This has to do with the data, essentially.
Yeah.
Because at the end of the day, it's just data.
Yeah, so the last slide essentially was there before. The database now we used to validate our idea was coming from the security domain.
I know, but at the end of the day, that's why I was surprised what you said in that slide. In the set, because this is just data.
Yeah.
If you've got good data on IDS, you've got one result. If you don't have good data on IDS, you've got bad results.
Yeah.
End of the day is completely abstract from the application area. So my point it was, why do you think that application area will affect your results, considering the assumptions you do about the data?
No, I'm not expecting that really the domain is impacting the strategy, because as you said, the strategy is high level. Problem is that I cannot claim that this is working in a domain different than intrusion detection if the data I'm using to validate my strategy comes only from the security domain. So I believe, so the way we try to set up the strategy is something which is not dependent on attacks on some specific domain. Problem here, up to this moment for this study, is that since at first we found mostly data coming from the security domain, those are the results we obtained by processing this attack dataset, then I believe that the strategy is working in a different domain, because we didn't have any assumption at the beginning about some specifics of attacks, but at this moment I cannot claim.
No, you make assumptions. But you make assumptions about the data. You might not make assumptions about the domain, all right? But you make assumptions about all the data is. And that's very clear in your paper. And because you make assumptions about the data, all right? If that assumption is matched in whatever application domain, it's fine, all right? But that assumption is not matched or not satisfied in the particular application domain, it doesn't work your experiment. You see, because the issue is that the assumptions you make about your data and not the application area that you're going to use that data. Why? Because at the end of the day, it's just data, it's just numbers. Nobody knows. Your pipeline doesn't know is the IDS, the intrusion detection system, which is drug detection, whatever. They don't know that. You're making up that. All right? Okay, anyway. I'm overrun by 10 minutes, all right? And I'm sorry, Tommaso, all right? Thank you very much for your talk. Thank you very much for all the participants which provide nice recordings. And thank you, Luis, Antonio, Ricos, for your only question from the audience. And I hope that in other sessions, there are more questions to come. All right, so I stop here. Andre, is that to you now? All right. And I leave you. All the best, you guys. Enjoy where you are. Unfortunately, can't enjoy Florianopolis and that very nice photo which is on the screen. All right. Bye-bye, everyone. I'll come out from this now.